In this video, we begin our study of Chapter 17, Chemical Equilibria. In this video, we're going to look at the equilibrium state of a chemical reaction. We'll look at the reaction quotient and equilibrium constants and some of their basic principles. We'll look at some principles for solving chemical equilibrium problems. And in our next video, we'll look at Le Chatelier's principle and perturbing chemical equilibria. As we saw in our last chapter on chemical kinetics, reactions can go in a reverse direction. All reactions are reversible, and under suitable conditions, they can reach a state of chemical equilibrium. Chemical equilibrium is the state where the concentrations of products and reactants no longer changes, not because the reaction is stagnant, but because the rates of the forward and reverse reactions are equal. Chemical equilibrium is a dynamic state because the reactions are continuing to occur, but since the reaction rates are the same in both directions, on average, there's no change in concentration or moles of reactants or products. An example of this is the reaction of dinitrogen tetroxide. Dinitrogen tetroxide decomposes into nitrogen dioxide, which is the brown gas in smog. Nitrogen tetroxide is a clear gas, and so this series of pictures of a bottle containing dinitrogen tetroxide illustrates the chemical equilibrium of this species. So on the left-hand side, we release the dinitrogen tetroxide into the vapor phase, and it immediately begins forming nitrogen dioxide. So the small amount of yellow color you see there is due to traces of nitrogen dioxide. Over time, the nitrogen dioxide concentration increases, and in the second panel you can see that the color is getting darker, and by the third panel the color is very dark. And at that point we've reached the equilibrium state, and the fourth panel shows us the color has stayed the same, and that shows us the reaction has reached chemical equilibrium. We can use this reaction to illustrate what we call the equilibrium constant. The forward rate equals the reverse rate. In this case, we know that the forward reaction has a rate that's equal to the rate constant for the forward reaction, K forward, times the dinitrogen tetroxide concentration, and the reverse rate constant times the nitrogen dioxide concentration squared is the reverse rate. When these two are equal, we can take the ratio of the two rate constants, and that will equal the concentration of nitrogen dioxide product squared divided by the concentration of dinitrogen tetroxide reactant. And the ratio of these rate constants gives us a new constant, which we call the equilibrium constant, capital K. The equilibrium constant relates to the product and the reactant equilibrium concentrations of a reaction. If K is a very small value, that indicates that the extent of reaction is in the forward direction is very small. If K is a very large value, that indicates the reaction goes nearly to completion. So we can take K as an indicator of the extent of a reaction. That is, how far it goes towards the products under a given set of conditions of temperature and pressure. So the bottom three panels show us three situations. The first one on the left-hand side is where K is a small value. It's shown as K is 0.02. So we can see that most of the material remains in the reactant state. There's very little product generated. In the second panel, K is a large value, and you can see that most of the material in the mixture at equilibrium is in the product state. And then the third panel shows us something where K is an intermediate value. It's a value of 1. We have equal amounts of reactant and product at equilibrium. Now we have something called a reaction quotient, and Q is a general term, and in fact this can be can take on any value for a given reaction. So let's look at this. For a general reaction where we have A moles of A, B moles of B reacting to produce C moles of C and D moles of D, the reaction quotient is defined as the following. It's the concentration of the products taken to the power of their stoichiometric coefficients divided by the product of the reactant concentrations taken to their stoichiometric coefficients. There's 3 stars next to this, so this is a key thing that you need to remember. This will turn out to be a key equation that we're going to use throughout the remainder of this semester. And you'll also use this in the future. This is a very important equation. Q gives the ratio of product concentrations to reactant concentrations at any point in a reaction. But there's a special case. At equilibrium, the reaction quotient equals the equilibrium constant. For a particular system and temperature, the same equilibrium state is attained regardless of the starting concentrations. So no matter how you start your reaction, once it reaches equilibrium, the ratios of their concentrations taken to the power of their stoichiometric coefficients will equal the same constant value. The value of Q can give you an idea under a given set of conditions how close the reaction is to being at equilibrium. So here we can look at the dinitrogen tetroxide reaction for 3 different sets of starting conditions. So on the left-hand panel, we can see that we start off with a concentration of 0.1 mole per liter dinitrogen tetroxide and no NO2. And over time, the system reaches equilibrium. The NO2 concentration rises up, the N2O4 concentration rolls off, and once we reach equilibrium, the ratios of the concentrations are 10.4. Now you'll notice that the individual concentrations can vary from condition to condition, but the ratios will be the same for each situation. In the middle panel, we start with excess nitrogen dioxide and no N2O4. Here, the reaction will go in the reverse direction. But once we reach equilibrium, even though the concentrations now of N2O and N2O4 and NO2 are different than they are on the first panel, the ratios are still the same, 10.4. Finally, in the panel on the right-hand side, we start off with equal concentrations of NO2 and N2O4. Let the system evolve over time, and once it reaches equilibrium, NO2 has risen up, N2O4 has fallen down, but the ratios of the concentrations are still 10.4. Now, when we have heterogeneous equilibria, we're looking at reactions that involve different phases. Heterogeneous mixtures, like we saw way back in Chapter 2, are where we have multiple phases present. So in a heterogeneous reaction or heterogeneous equilibrium, we'll have multiple phases. And an example of this is a very important industrial reaction, that is taking calcium carbonate, which is limestone, and if we heat it up, it'll produce calcium oxide and carbon dioxide gas. Now, a key point to point out here is a pure solid or liquid always has the same concentration. In general, for solids and liquids, we work with mole fraction. And so that is, regardless of how much we have, as long as there is some solid calcium carbonate present, its concentration will be approximately 1, because if we have pure material, its mole fraction will be 1. And the same for the calcium oxide. So the expressions for the reaction quotient and for the equilibrium constant will include only species whose concentrations change over time. At least that's how we will write it out. And so pure solids and liquids will be omitted from our expressions for Q and for K. Their concentrations, as long as they're still present, are always equal to 1, that is their mole fraction. So for this reaction, calcium carbonate going to calcium oxide plus CO2, the reaction quotient and the equilibrium constant simply equal the carbon dioxide concentration. We don't need to include calcium oxide or calcium carbonate. Here you can see a picture that illustrates this. We have two chambers, Both of them have the same carbon dioxide concentration because they're both maintained at 650 degrees Celsius. They both have some calcium carbonate and calcium oxide present. And the mole fraction within the solid for both of those is going to be 1. But you'll notice that in the panel on the left-hand side, we have more calcium carbonate solid, and on the right-hand side, we have more calcium oxide present. But all that matters is that we have some solid present for each of them, and then their mole fraction will be 1 within their solid. Now we can manipulate K and Q a variety of ways. The form of K and Q depend on the direction in which the balanced equation is written. So a reaction quotient or equilibrium constant, either Q or K, for a forward reaction is the reciprocal of the reaction quotient written in the reverse direction. This is an important principle to remember because you'll use this throughout the rest of this semester. So if I reverse a reaction, I take the inverse of the equilibrium constant. If I reverse a reaction, I take the inverse of the equilibrium constant. Now, if I decide to change the coefficients on the balanced equation, the equilibrium constant will also change. So whenever we write down an equilibrium constant, we always need to know how the reaction was written out in terms of its stoichiometric coefficients. This is one of the reasons that we often stick with the smallest whole number ratios, like we discussed way back in Chapter 3 in General Chemistry 1. That gives us a uniform standard for our equilibrium constants. If the coefficients of the balanced reaction are multiplied by a common factor n, that factor becomes an exponent for relating the reaction quotients and equilibrium constants. This is an important principle here. So if we multiply all of our stoichiometric coefficients by a value, say a half, then the equilibrium constant will be to the 1/2 power. Also, if we have an overall reaction and we add two reactions together to produce that overall reaction, the overall reaction quotient, or more importantly, equilibrium constant, is the product of the reaction quotients. This is important, and we'll illustrate this in some problem solving during lecture and on your homework. Here's a summary table showing how we can manipulate the equilibrium constant. So it's important to note that when we do chemical kinetics, you can't look at the stoichiometric coefficients and come up with the rate law. When we're doing chemical equilibria, we can always write down the equilibrium constants based on the stoichiometric coefficients. We don't have to use experiment to deduce it. It's implied by the stoichiometric coefficients, which is a very interesting and important principle. Now, moving on, if we have A as a reactant in equilibrium with B as a product, we can see the form that Q will take and the form of K. I'll focus on K in this case. Your equilibrium constant will simply equal the concentration of B at equilibrium over the concentration of A at equilibrium. If we reverse this reaction, the equilibrium constant then becomes the inverse of our first equilibrium constant. If we have n moles of A going to n moles of B, the equilibrium constant is going to be K to the n power for the new value. If we add two reactions together, and here we have A going to C, which has a given reaction quotient, and then C going to B as a reaction quotient, then the net, if we add those two reactions, is A produces B, and the overall reaction quotient is simply B over A, and that's the equilibrium constant. And finally, we remind ourselves that anytime we have a reaction or a product generated that is a pure liquid or solid, the concentration is unity. And so we can leave it out of the equilibrium constant. Next, let's look at how we handle gases. Gases have an interesting way of behaving, and they have an interesting equation. K for a reaction may be expressed using partial pressures of gaseous reactants instead of using molarity like we use with solutes. The partial pressure of each gas is directly proportional to its molarity, as we know. So we can take as an example 2 moles of nitric oxide reacting with 1 mole of molecular oxygen produces 2 moles of nitrogen dioxide. The reaction quotient could be written as the concentration of NO2 squared divided by the concentration of nitric oxide squared times the concentration of molecular oxygen. Or we could write this as what we call Q sub P, that is the partial pressure of nitrogen dioxide squared divided by the partial pressure of nitric oxide squared times the partial pressure of molecular oxygen. Both molarities and partial pressures are concentration units, and they turn out to be related to one another. And we're not going to go through the derivation here, but your book does a nice illustration on and derives this for you. The value for the equilibrium constant expressed as partial pressures is equal to the equilibrium constant expressed as concentrations times the product R times T, where R is the gas constant and T is the temperature, taken to the power of the change in the number of moles of gas from going from the reactant side to the product side. And so in this example here, we have 3 moles of gaseous reactants, that is 2 moles of nitric oxide and 1 of molecular oxygen, and we have 2 of our product, nitrogen dioxide. Therefore, we have a change in the number of moles of gas of -1. We start off with 3, we end up with 2. So 2 minus 3 is -1. And so the relationship of K sub P to K sub C is RT to the -1 power. The moles of gas don't change during the reaction. Delta N gas is 0. And then the 2 values for the equilibrium constant expressed in these different unit systems are equal. Let's look back at Q again. Q is a value that can take on any number, basically from 0 to infinity, and it indicates the current state of the system. So you may start off with a very small value for Q because you have a very small amount of product and you have a lot of reactants starting off. So that would tell you that Q was a small number and it was much smaller than K. So that tells you that the reactants are going to move towards products. So if Q is less than K, the reactants will decrease and the products will increase. The reaction will proceed as reactants moving to products until you reach equilibrium. If Q happens to be greater than K, that tells us we've gone past the equilibrium point. We're in a situation where the products are in excess. So the reactants will now increase and the products will decrease. The reaction proceeds in reverse direction. Reactants are going to be generated from products until equilibrium is reached. And if Q is equal to K, the system is at equilibrium. There'll be no further net change that takes place for the system. You can see this bar graph illustrates this. On the left, Q sub C is less than K sub C. Reaction will move towards equilibrium. In the middle, if Q sub C equals K sub C, the reaction is at equilibrium and there'll be no change. And on the right-hand side, if Q sub C is greater than K sub C, the reaction will move backwards towards reactants to get back to equilibrium. Now, what we're going to do next is look at just a few principles to handling problems with equilibrium constants. We're going to do a lot of practice problems. There are some in your books. There'll be plenty on your homework, and we'll also do some during lecture, and you can do some during recitation session. If equilibrium quantities are given, of course, you can just plug these into the expression for K and calculate what its value is. Now, in some situations, you'll be away from equilibrium, or you'll only have certain of the values, and you can use what we call a reaction table to solve this to find the equilibrium constant. And then in other cases, you'll be given the equilibrium constant, and you'll be trying to figure out the equilibrium values for your system under a prevailing set of mass balance conditions. So a reaction table will show the balanced equation, the initial quantities of reactants and products, potential changes in both the reactants and products, and then the equilibrium quantities. And some of these will be missing, and you'll solve them within a reaction table. So as a quick example, we can take the oxidation of carbon. So if we take carbon, that is graphite, in the presence of carbon dioxide at very high temperatures, this undergoes a reaction to form carbon monoxide. You can see the balanced equation. We have 1 for our reactant stoichiometric coefficients and 2 for the product. So we can see our balanced reaction is shown at the top of the table. The concentrations here for the gases are shown as pressures. For carbon, of course, carbon is a solid. Its mole fraction is 1 as long as the carbon is present, so we leave that out of our calculation of the equilibrium constant. The initial concentration, in this case, we have 0.458 atmospheres of carbon dioxide, and we find that at equilibrium, the total pressure is 0.757. So how will we get the equilibrium constant here? Well, we know that we're going to lose carbon dioxide and we're going to gain carbon monoxide. And for every mole of carbon dioxide we lose, we gain 2 moles of carbon monoxide. So we can put our change in as x, and then our product will be generated as 2x. And we can see at equilibrium we'll have 0.458 less the x value for carbon dioxide, and our carbon monoxide will be 2x. So we can see how that changes. And we can plug these into our equilibrium expression with our appropriate values. We can solve for this, and we can see that our equilibrium constant comes out to be 2.25 in this case. Equilibrium constants can be used in a variety of ways. We're going to use them throughout this semester. In some cases, we'll know K, some of the equilibrium constants, and we solve for others. Sometimes we know K, and we have initial quantities, and we solve for the equilibrium quantities. There's a variety of ways we can approach this. For your purposes, you'll either be given data to solve for the equilibrium constant, or in most cases, you'll be given the equilibrium constant. You can find equilibrium constant tables all over the place. They're very important values, and there are literally large volumes on equilibrium constants compiled by the National Institutes of Standards and Technology in the federal government. So they're important. Here we can see how you might approach this. Here we have a reaction, iodine gas reacting with chlorine gas to produce iodine monochloride gas. It's just a halogen switching reaction. We have our initial concentration. We have our change. In this case, we know the equilibrium constant is 9.09. This is a common case where when we put all this together, we end up with a quadratic equation. We can go through and solve the quadratic equation. Hopefully you guys are very comfortable with your basic algebra and solving quadratic equations. From this, we can come up with our equilibrium constants. You should work through this problem and similar ones using this. One thing you'll find is when you use the quadratic formula, you will get 2 answers. And as a very general rule, you'll find out that one of the numbers will often be either negative or chemically nonsensical, and so you'll throw that value out and you'll maintain the one that makes chemical sense. This is where you're going to have to start to build in what we call chemical intuition, when you will know, basically looking at the values, which one is reasonable and which one is unreasonable. And this will be based on the fact that you have to have positive values for all your molar amounts and concentrations for things to be meaningful. Now, there are approximations that you'll make, and we'll just list one of them here, we'll see that these will become very important when we're looking at weak acids and weak bases later on. If a reaction has a relatively small value for the equilibrium constant K and a relatively large initial reactant concentration, then, as would make sense, if it's a small value of K, you're going to generate a very small amount of product. And so in this case, if the initial concentration divided by the equilibrium constant is greater than 400, we find that you'll get an error of typically less than 5%. If you have initial concentration divided by the equilibrium constant is less than 400, you can't do this. It's sort of assumption. And you'll end up with a fairly large error. So if you have a situation where you have a large initial concentration, a small equilibrium constant, then oftentimes you do not have to use the quadratic formula. So here's kind of a flow chart for solving equilibrium problems in general. Some of this is just going to rely on you being comfortable at solving word problems, and we'll do a lot of practice problems in lecture and some with your Alex homework. You always start off writing a balanced equation. You can write out the reaction quotient or equilibrium constant for the system. You want to put all your amounts into units of either molarity or atmospheres, or in some cases you will be given a situation where you may want to use molality, but it will make it very clear if there is a situation where you need to use molality. But in general, molarity and atmospheres, or bar for gases. Then when your reaction direction is not known, you can compare Q with an equilibrium constant, or you might solve for an equilibrium constant. So you'll construct a reaction table, and then you'll substitute your quantities into your equilibrium constant value or your reaction quotient, simplifying math where you can, and do your solutions at that point. That ends this video, and next we'll move on to look at Le Chatelier's principle.